Mitchell, the theorem goes, there are, and we started looking at this last time in class, there are no, is there, okay, there are no integers m and n such that what? Oh, yeah. Such that, and this is, so it's from the textbook Belding and Mitchell. All right, folks, before I write the next statement, questions or comments? Okay, what did I say last time? I'm gonna underline this part. So this part is called, okay, which part do we have to prove? So last time I said that most theorems have an if-then statement. Here we don't have the if-then. So this is what I wrote in the class. I said we have if and then. We don't have that, right? It says there are no integers. So this is saying there do not exist integers such as m and n which can represent, there are no integers m and n that can represent a square root of 2 as a fraction. There are no integers. We can't find integers in the world that we put one in the numerator and the other one in the denominator, and that will represent a irrational number like square root of 2. Last time in the class, what I said was usually in these elementary textbooks, we run into theorems that go like this. Oh, this one's dying. Okay. And I said, which one? This thing or this thing? Which one do we usually have to prove to be true? What do we show? And the answer was the second one. Very good. And the second one is called conclusion or consequent. And the example that I gave was we wanted to show, for instance, the square root of 2 does not or is not a rational number. And then here, what did I do? I threw in a bunch of stuff that can be used. So if this is conclusion or consequent, this is called, according to our class on Monday. Anybody remember? No. Hypotheses or hypothesis, and the other name was antecedent. And so I recorded that. It's in the YouTube video as well, this part. And here, what did I do? In order to, and then what we did is we threw everything possible that we know that we can use to show this. Okay, so what do we know? We can use the definition of what? What is this? Rational, right? So something about rational we can use as in maybe the definition of Q. Because where does the, right? So I threw that in last time. A rational number is a number that looks like a fraction m over n. And this is rational. No. Is that what it is? No, this is wrong. I always forget the definition. Anybody? Where is Ryan? You're a math major, right? Oh, you're engineering. Okay. Should I just go m over n such that m and n are integers? So z, where n is not equal to 0. And I think that should work. Yeah, okay, all right. We also need to know what an irrational number is, but maybe not. Anyway, all the things. So what happens is, how does a theorem where so let's see. What we usually do is we want to prove this, and more than half of the proofs you're going to run into, or maybe even more, are indirect proofs, or actually proof by contradiction. So, and another name for this thing is, if it's a conclusion consequent, it's also, we can call it assertion. If the theorem asserts that square root of 2 is not a rational number, what we do is we assume the opposite of that and try to prove it. Okay, all right. Anyways, this is what I did last time. So now if we go back to theorem 1.111, I've underlined this bit here. And now I'm going to underline, what does this theorem want us to show? Yeah, so it wants us to show this is what we have to prove, to show, and then everything before that would be the stuff that we can assume to be true. So the way this is stated is saying that we can assume it to be true that there are no integers n and m. M and n do not exist. There are no integers that we put into a fraction form which will be equal to that. So we want to show, for instance, in this case, that square root of 2 is not equal to m over n. And in the other one, it was belongs. Square root of 2 is not in the set of rationals. If square root of 2 was equal to two integers, one on divided by the other, then we would call square root of 2 what? Rational. Why would we call that? Because it would be satisfying the definition of rational numbers, which is that rational numbers are two integers, m over n, where m and n are integers, and the bottom one is not equal to 0. Okay, all right. We got to move on because I'm spending too much time on this. Here's another formulation of the same theorem. This is by Mr. Abbott. And he says that there is no rational number whose square is 2. So apparently, this is yet another way to say what Mr. Belding and Mitchell says. So this is from Abbott. So he says, so let's think about what he's saying. So there is no rational number. There is no rational number. Let's say it is Q, whose square equals square root of 2. Is that what he just said? So there is no, this does not exist. And if you square it, you're not going to get that. Is that what, and that's what we have to show in this case. Okay, so let's see. Because, right, if you square both sides, Q equals 2. Q does not, there is no number that, okay, all right. I don't really understand. Does everybody get that? I don't really get this one, but yes. Oh, rational numbers. So sorry, I messed that up. Let's try this again. It says there is no rational number. So what's the best representation of a rational number? That's a rational number. You can also say Q is a rational number, but this is what we should be using, right? Hint, hint from the other formulation. So now we're good. Thank you. So now we're better. Now I can understand it. There is no rational number m over n whose square equals square root of 2. Yes. So okay, so I think your question is, there is no rational, m over n does not exist. There is no such fraction that if you square it, it will equal square root of 2. That's what it's saying. Okay. Which means that, okay, so there's that. And again, we have to prove that. We have to prove this in this case. All right. Now, the third formulation is the one that we're going to prove. And this is from this professor at Riverside, UC's Riverside. And he says, this is from his lecture. So this is what he wrote. He said, we're going to prove this one. What does this say? The square root of 2, which is an irrational number, is not a rational. Square root 2 is not a rational. Okay, so let's do this. Okay, all right. And so this is very like, it's not in the if-then form. All it is giving is a result and telling us, please prove this result. So what we have to do is bring all our knowledge about rational and irrational, the definition of rational numbers, the definition of, on Monday, I talked about even numbers. The definition of an even number is a number that is represented like this. So every even number has a 2 inside it. Okay, and k equals, when k is 1, do we get an even number? 2. You bring k in, so 2 times 1, 2, right? Okay, when k is 3, do we get an even number? 6. When k is 2, do we get an even number? So this, any even number can, so let's put here, even number. This is how we can represent an even number. How do we represent a rational number? Where both these are integers, right? And where n is not equal to 0. How do we represent even numbers? 2k, or we could also say 2n, where n equals 1, 2, 3, or k equals. So what's that? Any integer. What are integers? -3 all the way to -infinity, -2, -1, 0, 1, 2, 3, all the way to the right side. So here we can replace m by a negative number, by a 0. Here we cannot replace n by 0, but we can replace it by negative numbers and positive numbers. And here k can only be replaced by, what is this 1, 2, 3? Where k is a natural number. Yes? Right? Over here we can say m, comma n belong to the integers. All right, so this will come in handy. This understanding of even numbers will come in handy in the proof. So I'm going to now delete all this. Emma, are you almost good? I can erase? Yes? Okay. All righty. So let's do the theorem. And this is, it's supposedly the easiest theorem in the book, but I don't know. So let's see how difficult it is. I think we are primed for it because we've been thinking about rational numbers and irrational numbers and integers for like the last 3 weeks or something. So here's the theorem. And the theorem goes, this is Avi Sensor's theorem, professor. This is how he presented it, so I'm just using him. That's his spelling. There's some videos on calculus. online by this guy. Very, very good. From 19, I don't know when. Okay, here we go. Okay, how do we, so we're going to do what? Is this true? It is true. So what we do is, we're going to do proof by contradiction. Because when you see something like that, you're like, I don't know, let's just do proof by. And in proof by contradiction, you go to the conclusion, assert the opposite of the conclusion, and you start there, right? This is the conclusion of the theorem. So we're starting there. So the proof is by contradiction. All right. So let's assume that square root of 2 is a rational number. So this symbol is what? Belongs to, in, right? So you can also just say is. Square root of 2 is a rational number. If it is a rational number, what's the next step? This is where you bring in the definitions. So I'm going to write here what we just did. We did what? Assumed the opposite of the assertion, theorem's assertion. That square root of 2 is a rational number. Next, we're going to use at this point, you go, okay, what do I know? What can I use? Let's apply the definition of Q to our new, let's apply the definition of Q at this point in the proof. Okay. So everybody remembers the definition is Q, rational numbers are M over N such that M and N belong to integers where N is not equal to 0. All right, so if this is a rational number, it should look like that there exist two integers that one place in the numerator in the denominator represents are equal to this thing, literally. So square root of 2. So this is our second line equals M over 2. Oh, sorry. M over N. So I'm using small m and small n. Okay. Once you've written that, you're like, okay, have I got anywhere yet? I have to get here. So where do we have to get there? How do we get there? We say that if we assume the opposite of what is the truth, and we assume the opposite, then we're going to run into a contradiction sooner or later, okay? And in this key thing, the contradiction comes out of the form of this thing. And so we have to make another assumption. We're going to assume that square root of 2 is equal to M over N plus here M over N is in reduced form. Reduced forms means that we can't cancel common factors out of it. Okay, so if M was even, if we keep going and we find out that both M and N are even, that means we can take 2 out, because every even number is of this form. There's always a 2 lurking in it. What will happen as we do this proof is that we find out that if we assume this to be true, we end up saying that both M and N are even numbers, which means they're not in the reduced form. And so we have a contradiction. That this assumption turns out to be wrong. Therefore, our decision to take to say that the opposite of what the theorem is saying is true was a bad idea, and therefore we have proven that this is true. There is no direct proof for this. The direct proof would be you start from assumptions and go and produce the consequent. Okay, all right. So we've got, this is what's going to break. This is going to break. We're going to, okay. Now that we have our second line here, what do we do? If you remember some of the theorems, yes. Oh, I see. No, we have already assumed that you, oh, like 2n here. So the definition is m and n are any integers, not necessarily even. What will happen is we'll find out as we go through that that if we assume this incorrect statement, then this will turn out to be an even number over even. We will get there. You will have your 2. So actually very fast. It's sitting right there for you. So you go, okay, what should I do? There's another thing that we will be using, which is, so we'll be using this idea. And the other idea is that an odd number times odd gives you odd. And an even number times another even number is going to get you another even. That's another main idea that we'll be using. So at this stage, you're like, okay, I need to do something to this so I can get somewhere. And I do something to that so that it doesn't change. The equality stays the same. So we can do, we could square both sides, which gets us 2 here, m squared over n squared. And we're like, okay, what's next? Well, we could do what Emma wanted. We've got this. Yes. No question is dumb question, usually. Yes.
So, okay, if I were to like grab a square root
Oh, fourth. So we have, oh, no. So square root of 2 is a irrational number. Yeah, so or this, we could have pi over here or something. But here we're using, the other thing is that, yeah, okay, no. So we're dealing with an irrational number, pretending it isn't, by equating it is into this. Actually, so let me leave this here. And then, okay, at this stage, what you do is, maybe I should do some operations. What are certain operations you can do at this stage? Oh, no, not like that, but doing something like doing things to this equation, this equality that doesn't change it. Hey, I might just add 1 on both sides. Is that Jalen? So are you trying to get into this class or? So, and you send me this document thing. So just email me and I'll get you in. Okay, yeah, all right. I mean, if you want to. Okay. Were you my past student or? Back in the day, right? Okay, so this is like we do math and stuff, so you're okay with that? Oh, okay, all right. What's your major? Very good. Okay, we have a lot of English people here. I'm English. Just, oh yes. So that's my Englishness right there. The equality stays the same. Will this help us? Not really. Because we want to do something to this so that we can talk about this form and this thing. Because we want to show that our m and our n have to be even, which then means that they're not in the reduced form. And therefore, this whole exercise was wrong. In the PowerPoint, I'm going to send you the PowerPoint after the class. M is on this side and 2n squared is on this side. Should we do that? Doesn't matter, right? But we can do, let's just, let's do, okay, let's just, this is fine. All right, what's the next step? Well, we want to think, because we want to prove that M has better be even and N better be even. M better be even, N better be even, which means that this assumption will be wrong. So our next step is we're going to say that M squared is even. Okay, so why can I say that? So I'm going to write the because M squared equals, what does it equal over here? 2n squared. And 2n squared is an even number. Why is 2n squared an even number? Because it is divisible by 2. Is an even number cos 2n squared is divisible by 2. So if the left-hand side is even number, then the right-hand side, and if it's equal to the right-hand side, that has to be an even number. There is no way an even number equals an odd number. Okay, and 2n squared is even because we can divide it by 2. Any number that is divisible by 2 is an even number. That's another definition, including this guy here. This is even because if you divide it by 2, it is divisible. There's no remainder. Okay, so now we got M squared is even, but our goal is to find to get to where we can say M is even. And why is that? The square of an even number is always an even number. The square of an odd number is always an odd number. Therefore, if M is a square of something and we have established that it's even, that means it is probably made up of 2 even numbers. It has to be. So we go, first we say M squared is even, then we go an even number can only be a product of 2 other even numbers, right? So therefore we can say that. So then the next line is M is even. So why is M even? Because otherwise this wouldn't be. This thing has to be made up of 2 even numbers, not 1 odd or 1 even, like 3 and 2. This cannot be 3 and 2 because this is just 1. So it cannot be 3 because 3 squared is what? 9. Is 9 an even number? No. How did we establish M squared is even? Does anyone remember? Because it is equal to an even number right here. Once we M squared, so we concluded M squared is even because we said that the left-hand side has an even number, which is, and it is even because it's divisible by 2. So now even M squared is even. And then we are saying that if M was odd, for instance, 3 times 3 is 9, that is odd. It has to be 4. 4 times 4 is 16, that's even. 2, it can be 2. 2 times 2 is 4, which is an even number. Therefore, M has to be, this little m has to be even. So this is our first important result. We have now come up with that the numerator is even if we assume this condition to be true. If we assume the square root of 2 is a rational number, and it can be represented like this, that square root of 2 is equal to m over n. In this case, this fraction, this rational number, the square root of 2 is equal to, the numerator is an even number. Now we just have to prove that this is also even. And if both are even, that means they have a common factor. And which one is that? 2 for sure. the number 2. You can divide 2 without m without a remainder, and then if n turns out to be even, we can divide n with 2 without a remainder, which means this condition is not being respected. Okay, now we have to do, so we're done with the first part here. So this is our first part, let's call that. And maybe I can do it up here. Let's see. So we're going to go from here all the way up here. Now we have to show that n is also even. So how do we do that? We go, well, I have to cheat now. What does he do? Oh, he just does that. Okay, all right. So he also makes another. So he says m is even, and then he does something else too. Does he do that? Okay. He makes another assertion. Not only is m is even, which the professor does that, but he also says a second thing, which is that m squared is divisible. And this is a key, tricky bit here that I wasn't thinking, and I had to cheat, is divisible by 4. Is that true? If m squared is a product of 2 even numbers, each of those 2 even numbers are divided by a 2 and a 2. So together you can divide it by 4. Well, let's just test it. If it is 2, you get 4, right? 2 is even, you get 4, you can divide it by 4. If I put in, let's say, 4, you get 16, you can divide it by 4. 3 is not an even number, so I can't put it in here because m is, I was going there in my head, I was thinking about 3. Okay, now let's do the other side, and we have to do this. 4th thing is kind of crucial apparently, and I don't like it, but that's how he did it. So what can we say about this guy here? First thing we can say is that 2 times n, so the left-hand side is, can we say that it's divisible by 4? We can't. We have to. Okay, so why can we say that? I don't know. This could be what, 2? Well, 4, yeah. If n was even, we don't know at this point, we don't know n is even. Okay? If n is not, at this point, all we know is we have we are making this assertion that 2n times square is divisible by 4 because we made a statement here that the right-hand side is divisible by 4. If these two guys are going to be equal to each other, if you're saying this is divisible by 4 and it's equal to this number better be equal to, better be divisible by 4, otherwise they're not equal to each other. Because they're equal to each other, this guy is divisible by 4, therefore we can say that 2n raised to power 2 is also divisible by 4 because 2n squared is equal to m squared, which is divisible by 4 as shown below, right here, or stated below. Okay, so if you're getting lost, what we did is we showed that m is even and m squared is equal to 4, and which means this is divisible by 4. We still haven't shown that n itself is even. So what is the next step? I have to cheat. Now, can we say that n squared, so if this is true, can we say that this is the result of saying that is divisible by 2? Why can we say that? So if we take 2, 4 is 2 times 2, it gets rid of this instantly, right? So if we take this number here, 2n, and we divide it by 4, and we are saying whatever the result is, there's no remainder. It's a clean, it is divisible. These two will cancel, and this will be also a clean division without a remainder. So what this is saying is the 2 in the 4 cancels this guy out. This also divides, and if a number is divisible by 2, that number is even. Very good. N squared is even. Okay, who's lost? Raise your hand, ask me right now. Yes, Jalen. Well, you missed the first 3 weeks too. So there is the pizza Saturdays, where I'll go in more deep with more topological stuff. So, huh? Every Saturday until I run out of money. But I have a credit card. So if I run out of money, I'm going to start charging it. So it's every Saturday, giant pizza from Costco, noon, and I'm going to send out an email on Friday. Yes, there is, we can do half-half.
Oh, yeah, actually, yeah.
Yeah. So, but it's going to be cheese, basically, and then you can have some other toppings. Okay. All right. If n squared is even, can we say that, what does the book do? Not the book, the professor. And he goes, n is even. How can we say that? If this is even, 2 even numbers multiplied to each other do not give you an odd. They give you even. Therefore, n is even. So now these are the 2 things that we wanted to prove, to show if we assume this to be true. Now both m and n are even, which means they have a common factor. And this important thing, that the square root of 2 equals the reduced form, that you cannot reduce any further this fraction, which means it would be rational. This is not true. Both of these can be divided by 2. And therefore, our assumption is wrong. And the statement of the theorem, which was that the theorem is this, that the square root of 2 is not a rational number, is correct. So we reached a contradiction. We got a result that contradicted this assumption. We got 2 results. Both the numerator and the denominator were even, and that contradicted this assumption. Because a reduced form fraction cannot have an even number divided by an even integer over another even integer. Because being even means you have a 2 inside you already. So 2 is always a factor. That is a common factor. Reduced form means that m and n do not have, so you should add that if you're taking notes, have a common factor or have common factors.